Acids and bases, they are all over the place, whether it's vitamins, your own blood, soap, what's going on in your stomach, fruits, food flavorings, so many things are either an acid or a base. So just what makes an acid, what makes a base a base? Arrhenius was one of the first guys to investigate this. And interesting guy, right? Taught himself to read at the age of 3. Crazy, right? He got a doctorate degree. He ends up winning a Nobel Prize, even though he got a D on his dissertation. Kind of interesting. But Arrhenius is the guy who gave us this idea. A lot of hydrogen ions, you're supposed to think of acidic. If you have a lot of hydroxide, you're supposed to think, basic. So he really got things, going. So what really exists in water? Is it hydrogen ion or this hydronium ion? Well, the animation might help. It's not so great, but the idea here is you have hydroxide, reacts with hydronium ion, makes a couple waters. But notice how nowhere is there floating around a bare proton. Nowhere is there an H+. It always exists as H3O+. So, but for our intents and purposes here, we can use and get by with H+. And it gives us all the right answers. It's easier to write. You don't have to worry about adding this extra water all the time. So we're kind of just sticking with it, even though it really doesn't exist in water. So Arrhenius gave us the idea of hydrogen ion, acid, hydroxide, base. Okay, but life became more problematic. For example, ammonia had basic properties. And then we had acidic properties in solvents that didn't even have hydrogen ions. So we need more than one theory than what Arrhenius came up with. This is ammonia reacting with water. And notice how it forms ammonium and hydroxide. So since it formed hydroxide, that means ammonia, in the first place, is acting like a base, right? Because it's producing a lot of hydroxide. And what's kind of interesting, what we need to get used to doing, is recognizing acid-base pairs. So here's ammonia. What's its pair? Ammonium. So this is the acid form, and this is the base form. How you tell the difference is the acid form, the acid form just has more H's. It has 1, 2, 3, 4 H's. The base form only had 3. Okay, and we're going to get into that pretty much now. So we need 3 acid-base definitions to take care of all the acids and bases that we know of on the planet. So the first idea here is what Arrhenius gave us. And we talked about when an acid is placed in water, it produces a lot of hydrogen ions. When a base is put in water, it produces a lot of hydroxide anions. Okay. Hydrochloric acid is a good Arrhenius acid. Show you what I mean. Here's hydrochloric acid, HCl. When you put it in water, it forms our hydronium ion, because H+, right, reacts too quickly. We just form hydronium ion, and we're left with our chloride anion. So again, our acid-base pair, here's our base form, here's our acid form. HCl, acid form, Cl- base form. We'll get some names for these pretty soon. Lewis, the second theory. An acid is a species that accepts or donates electrons when forming a covalent bond. Okay, how I keep these things straight is I know all these theories really have to agree with one another. So I always think of that Arrhenius idea, right? H+ I think of as my acid. I think of hydroxide as my base. Okay, that's what Arrhenius was talking about. An acid can do what? Accept or donate electrons. Well, I have H+. It's positive. All positive can accept electrons, right? A base is a species that, here's my base, it's negative, donates electrons. That's how I keep these straight when forming covalent bond for a Lewis acid or base. Bronsted-Lowry, an acid is a species that donates hydrogen ions. Again, I'm just following my Arrhenius idea. A base is a species that accepts hydrogen ions, okay? Like hydroxide. It could accept a hydrogen ion and make water. So that would make hydroxide a Bronsted-Lowry base. According to Bronsted-Lowry, blank acid-base pairs differ by the presence of one proton. Here's a good example. Hydroxide and water. They just differ by one H+. They're called conjugate acid-base pairs. So let's take a little practice here. Identify the conjugate acid-base pairs in the below acid-base reactions. So that's not too bad. Fluoride has to get paired up with hydrofluoric acid because they differ by one H+. Hydronium ion and water. There's my conjugate acid-base pairs. How about B? Acetate and acetic acid. Ammonium is a conjugate pair with ammonia. Write the balanced reaction of hydroxide with hydrofluoric acid to form fluoride ion and water, and then identify everything as an acid or a base. Okay, so what is reacting with what? We have hydroxide is reacting with hydrofluoric acid to form the fluoride anion and water plus H2O. Okay, now let's identify things as acids and bases. Well, hydroxide, remember, definitely a base. Well, if hydroxide is acting like a base, this has to be acting like an acid because bases react with acids, acids react with bases. Okay, so we have that side's done. If HF is an acid, this must be a base, right? Because they're conjugate acid-base pairs. If hydroxide is a base, water must be acting like an acid here because they're conjugate acid-base pairs. You kind of also tell too, for example, like look at these two. They differ by an H+. Here you have an H+ there, so that has to be the acid form. Give the conjugate base to each of the following species, regarded as acids. So we want to give the conjugate base. So we have to remove an H+. Because these conjugate acid-base pairs differ by an H+. If we want the base form, we have to remove an H+. So let's do that. Let's remove a hydrogen ion. Well, we're left with NO2, but NO2 minus, right? Because you have to remove a plus charge too. Remove an H+ from the next one. You're left with only one hydrogen. And that -1 charge is going to get reduced to -2 because you have to remove an H+. So give the conjugate base. So here's our answers, those two. Give the conjugate base again for these compounds. So again, they want the conjugate base, so remove an H+ in each case. So there's our conjugate bases. Give the conjugate acid to each of the following, regarded as bases. So now we want to give the conjugate acid. You want the acid form, so you have to add an H+. And then we'll have the acid form. And whether you put the H out front or at the end. It really doesn't matter. Usually they like to write acidic hydrogens first. Add an H+. Now I have 4 hydrogens, but don't forget to write the plus because you're adding an H+. For the following reactions, label each species as either an acid or base. Okay, let's do that first. So we have ammonium. Maybe we should do the conjugates first. Indicate the species that are conjugates of one another, because that really helps. If we find the conjugates, it's really easy to tell who's acidic, who's the acid, and who's the base. So you have ammonium and ammonia. Which one is the conjugate acid? Ammonium is. Right? It has more hydrogens. So that means this must be acting like a base. And now everything falls together. If ammonium is acting like an acid, this hydrogen, monohydrogen phosphate, has to be acting like a base. And if this is ammonia is acting like a base, this has to be acting like an acid. Okay? So here's another conjugate pair. Okay. Do the same thing for C. Identify the conjugate acid-base pairs. Determine who's acting like a conjugate acid, who's acting like a conjugate base. And it will all come together after that. Hydronium has 1 more hydrogen ion, so there's my acid form. That means this must be a base form. Water must be. If hydronium is an acid form, this must be acting like a base. This is acting like a base. This must be acting like an acid. So here's my other conjugate acid-base pair. Write the Lewis electron dot formulas of the reactants and the product and identify each reactant as a Lewis acid or a Lewis base. So this idea of, remember, Lewis acids and Lewis bases? That was a Lewis acid because it can accept electrons. Lewis base because it can donate electrons. Okay, and making these bonds. So it's a lot easier to see this transfer of electrons if you draw the Lewis electron dot formulas. Now you're doing pretty good if you remember how to do this. Boron goes in the center, it's surrounded by all these 3 fluorines. Okay, that's the first step in writing the Lewis electron dot formula. We have to figure out the number of valence electrons. Boron, number of valence electrons. Boron has 3 on the periodic table. It's in group 3. Fluorine, each one has 7. So I have 3 fluorines. 3 times 7 is 21 plus 3 is 24. Okay. When you're making these Lewis electron dot formulas, first thing you do is connect them. Make octets on all the surrounding atoms. If you have any electrons left over, put them on the center atom. So let's make octets on all the surrounding atoms. If we have anything left over, we'll put it on the boron. So each fluorine has 8. There's 3 fluorines, 24, and we're done. We used them all up. Lewis electron dot formula for fluoride. Okay, well, fluorine has 7. You have to add an extra one because it has a negative charge. It should have 8. Fluoride should have 8. Then remember, when it has a charge, you're supposed to draw a bracket and write the charge. Okay, that goes to boron tetrafluoride, the -1 charge. So it's going to be very similar to what we did here. We're just going to have 1 more fluorine. That'll give us another 7 electrons with an extra charge, right? Add 1 more. So really have an extra 8 electrons. Well, that's just 1 surrounding fluorine, right? That's just an extra 1 of these. 2, 4, 6, and 8 with the bond. So we just added it. So let's write in the other ones. need our brackets with our -1 charge. Okay, so we are supposed to identify each reactant as a Lewis acid or a Lewis base. So this fluoride, now you can kind of tell already, it's got a negative charge on it. That's going to be our Lewis base. The fluoride will be. But let's see how this is working. Right? It has a negative charge. It's got to be our Lewis base. So that means this has to be our Lewis acid. But let's take a closer look just to prove it to ourselves. So Lewis base, it has to be donating a pair of electrons to make a covalent bond. So it's just taking these and donating them. Right? It's making one of these bonds. So it donated a pair of electrons to that boron trifluoride. The boron trifluoride accepts the electrons, so it acts like the acid. Okay, so our base and our acid. In the following reactions, identify each reactant as a Lewis acid or Lewis base. So again, and I don't think you have to write Lewis dot formulas, because anything positive, remember, is our Lewis acid. If it's negative, it's going to be our Lewis base. That's how I figure these out. So copper +2, water could go either way. But look at copper 2. It has a positive charge. That has to be my Lewis acid, right? Acting like H+. Well, if copper 2 is my Lewis acid, this has to be my Lewis base, my other reactant. Okay. Try the same thing on the next one. See if you can figure it out. Which one is the Lewis acid? Which reactant is the Lewis base? Chloride has a negative charge. That has to be my Lewis base, right? It's acting like hydroxide. So that means tin chloride has to be my Lewis acid. And that's it. So to handle the homework, I would just have a good, solid understanding of the 3 different theories, right? Where you have Arrhenius, Lewis, and Bronsted-Lowry theories of acids and bases.